In this video, we're going to talk about a bunch of graphs for functions that we should probably be comfortable using, so knowing what the shape looks like. And then we're also going to talk a bit about piecewise functions. Okay, so the first one is the function f of x equals x. Okay, now this is actually just a line. Okay, so what the graph for f of x, we actually know this is in slope-intercept form. So it's 1 times x plus 0. So the y-intercept is 0, and then the slope is positive 1. So this line is going to look like that. Some properties for these. The domain is, of course, all real numbers. The range is also all real numbers. This is an odd function, so it has odd symmetry. Oops. Okay, so if you plug in negative x, you get negative f of x. Okay, this is origin symmetry. It's a linear function, okay, because it's x to the power 1. And it's increasing on its entire domain. Okay, so the function here is always increasing. Now, this function is known as the identity function, because if you plug in any x value, you just get the same x value back out. Okay, let's move on to a harder one. So f of x equals x squared. Okay, so hopefully we know this one. The shape is what we call a parabola. Okay, so it has its vertex at the origin, and then if you go out 1, you go over 1, up 1 on both sides. If you go out 2, you go up 4 on both sides. So the graph, has a shape, something like this. Okay, it's sometimes called the square function. Okay, now some properties. Again, the domain is all real numbers, or negative infinity to infinity. But now the range, the range is my r, it only hits all the positive or non-negative numbers, so it goes 0 to infinity. It's an even function, so it has y-axis symmetry. And then it's decreasing. Okay, when we go down to the right. Okay, so that's on that side. So it's decreasing from negative infinity to 0, and then it increases after 0. Okay, so on 0 to infinity. And in fact, there's a local minimum at the point 0, 0. Okay, so that's all about the function f of x equals x squared. Okay, now if we have f of x is x cubed, so this is the cube function. Okay, it also goes through 0, 0, but the shape of this one looks like that. Okay, so something like that. So domain, all real numbers. Range is again all real numbers. Okay, this one is an odd function. Okay, so if you plug in negative x, you get negative f of x. Okay, so again, that gives you origin symmetry, which we can see from the picture. It's always increasing. So negative infinity to infinity. And I put the intercepts on here. So x and y intercepts, both at the point 0, 0. There's no local max, local min. So that's what that one looks like. Okay, now we have the square root function. Okay, so before I draw it, let's just remember that the domain here, so I can't plug in negative numbers because I'm doing square root of x. So it's going to be from 0 to infinity, but I could plug in 0. And it actually has this sort of shape. Okay, so notice that there's nothing for when x is negative. So the domain is that. The range is also from 0 to infinity, so we only get positive numbers out of the square root. The x and y intercepts are at 0, 0. Okay, both of them. This function has no symmetry. Okay, so it's neither even nor odd. Because if you have a positive x value, the negative one is definitely not in the domain, so there's no point there. And it's increasing on its whole domain. So it's increasing on 0 to infinity. And then we have the cube root function. Okay, now when we have a cube root, now we can actually plug in all the x values. So our domain goes back to being all real numbers. And in fact, the range is also all real numbers. This one is an odd function because if you have the square root of negative x, that's negative the square root of x. And what you get for this one I didn't do it right. It kind of looks like that-ish. It's actually more vertical in the middle here. Okay, so something like that. So it looks like that there's horizontal asymptotes, but there's not. Okay, so these things do go to infinity. It's an odd function. Again, x and y intercept is at the point 0, 0. And it's increasing always. Okay, so it's increasing on its full domain. So that is, actually I do want to redraw this, I think. Okay, so it grows really slowly. It looks something like that. So those are a few functions that we're going to be working with. You should have their basic shape in your mind so that we can do other stuff with them. Okay, there's a few more complicated ones. So f of x is 1 over x is called the reciprocal function. Okay, and here the domain does not include 0. Okay, so I'm just going to write x not equal to 0. But in interval notation, it would go negative infinity to 0, and then 0 to negative infinity. The range is actually the same. So y is never 0. This one actually has asymptotes. Okay, so it has a vertical asymptote at x equals 0, and it actually has a horizontal asymptote also at y equals 0. Okay, so we get those asymptotes there. And its shape, so it looks like that shape on the positive side, and then it has a similar shape on the negative side, but in the negative part. Okay, which means that it is an odd function. So you can see the origin symmetry that it has. Now this function decreases on the interval from negative infinity to 0, and then again on the interval from 0 to infinity. So on its entire domain, it's decreasing. So as we move to the right, we're always going down. Okay, so you can't include this jump at the asymptote there. It's not counted as increasing. Next, we have the absolute value function. So here, remember we can plug in anything into the absolute value. So the domain is all real numbers, but we're only going to get positive numbers out. So the range has to be from 0 to infinity. This one is going to be an even function. So it has y-axis symmetry. And what it looks like is a V. Okay, so it looks like that and like that. Okay, so on this side, this is the line y equals negative x, and on this side, this is the line y equals x. Okay, but that's what the absolute value looks like. So it's decreasing on the interval from negative infinity to 0, and then increasing after 0. And here we have a local minimum at the point 0, 0. Okay, so local minimum of 0 at x equals 0. Okay, finally we have the f of x equals b. So b is just a constant. Okay, so this is a constant function. Okay, now here the domain, so we can plug in anything into this because there's no x, nothing bad can happen. But the range is just the value b, right? Because we always get a b out. So we're going to have a y-intercept at the point 0b, no x-intercept, unless b happens to be 0, then obviously we'd go through the point 0, 0. This is an even function because there's nowhere to plug in negative x. Okay, and then it would look just like a horizontal line. Okay, so this point is at 0b, whatever b is. And this one is not increasing or decreasing. It's what we call constant. So it's constant on the entire domain. So it's always equal to b. Oops. Okay, so those are a few ones that we want to be comfortable with. Now, piecewise defined function uses a couple of functions usually, and puts them together into one. Okay, so a function is a piecewise defined function when it is defined by different equations on different parts of the domain. Okay, now an example could actually be the square root function. Okay, so if we had y equals square root x, you can define that as a piecewise function. So if x is at least 0, then the square root doesn't do anything, so we just get x back. But if x is less than 0, then you're going to have negative x down here because x is negative. Okay, so here x is less than 0, which means that negative x is actually bigger than 0. Okay, so that's how you can make a positive number without using an absolute value. So it looks like a negative number because of the negative out front, but what you want to remember is that here x is negative. So negative negative makes a positive. Okay, so that is an example of defining a function as a piecewise function. Okay, so let's see more complicated example. So we're going to graph this. So I'm going to do the first one, and I'm going to leave the graph of g of x for you. So if x is less than negative 1, Okay, so I'm going to just put -1 is where we split. Okay, there's not an asymptote here, and I am going to try and erase this later, but just so we can keep track. Okay, so on this part is x squared, so we're going to have a parabola over here, right, because that was a square function. Okay, now between -1 and 1, we have the function 2x minus 1. Okay, so in this interval, it's 2x minus 1, which actually is a line. Okay, and then on the last interval, so when x is bigger than 1, it looks like the square root function. Okay, so that's how we're going to break it up. So it's probably easiest to start in the middle because we know around the origin. Okay, so if y, so in the interval -1, -1 is less than or equal to x, which is less than or equal to 1, we're using the function y equals 2x minus 1. So that is in slope-intercept form. So that means the slope is 2, and the y-intercept is the point 0, -1. Okay, so that's in my interval. So I know I have a point here, and then I have a slope of 2. So I'm going to go up 2 over 1, down 2 over 1 to the other way. So I know that I have points there. And now my interval includes -1 and 1. So I have closed points there. Okay, so on this interval, I have the line that connects those 3 points. Okay, so it's going to look like that on that interval. Okay, now in the interval x is bigger than -1, we're using y equals x squared. Sorry, less than -1. So maybe you want to plug in, so at -1, okay, the y value is -1 squared, so +1. Okay, now this point is actually not on the function because our interval doesn't include -1. Okay, we actually already have the point at -1. It's at -3. But what we are going to get there is a hole. So at -1, 1, so up here I have this hole. Okay, now we know the shape of the parabola, y equals x squared, or f of x, so it goes like that, and then it continues like this. Okay, so we only want to draw the part that's in our interval. Okay, so we know that it actually, here, let me just switch colors. So it actually goes like this. Okay, but we don't want that green part. Okay, because we're only on the interval from when x is less than -1. So let's get rid of that. Okay. Oops. I'll make that line again. Okay. And now when we're bigger than 1, okay, we have y equals root of x. Okay, so at x equals 1, y is going to be root of 1, which is 1. Now, that actually meets up with the point that's already there. Okay, so that's nice. And then our square root function goes through that point, and then it continues like this. Okay, so we only want that continuing bit. Okay, so on that part of the interval, we have the square root function. Okay, now I'm just going to erase all these lines I made because I don't actually want them. I don't have an asymptote. Okay, that was just helping me split the interval. And I don't need that purple part or the slope, I guess, how I computed the slope. So this is what my function is going to look like. So notice when you have a piecewise function, where the pieces meet, so like at -1, I could have a jump in the graph, right? Because they didn't go to the same point. But at 1, they did actually go to the same point. So that's where I don't have a jump, where they actually meet in the point. Okay, so there's two things that can happen at each interval change. Okay, so that is what my function would look like for this. So I have a parabola, and then I switch to a line, and then I switch to a square root function. Okay, so now I'm going to leave G, the graph of G for you, and a few questions about G, and also this word problem. Okay, so take a chance at those. See how you do. I know piecewise functions are challenging for people. That's why I wanted to give you one to try before you see the answer. Because once you see it, it normally makes sense. Okay, so these are the functions that we want to have ingrained in our mind, what this sort of shape looks like, because we're going to start doing stuff with them.